webcast is now starting. All attendees are in listen-only mode.
Hello, everybody, and welcome to today's webinar, Off-Grid Masterclass. My name is Tim. I'm from Half Moon Education, Inc., and I will be your moderator for today. This webinar will run for 3 hours and 15 minutes, and we'll have a 15-minute break somewhere around the halfway point. Before we jump into the content, I do just have a few notes to go over. First, as a means to prove attendance in the event that either you or Half Moon Education is audited by any licensing boards, please be sure you're logged into the webinar using your own individual internet connection. As an extension of reporting accurate attendance, there's going to be a brief quiz at the conclusion of today's webinar. It's not long. It's not meant to catch anybody up. If you're having any problems with it, call into our office or reply back to any of our emails, and we can help you out with that there. Included with the quiz is an evaluation form. We do appreciate any feedback you can give us regarding our webinars. So if you do have time, fill out the evaluation to the best of your ability. We do greatly appreciate it. Certificates of completion will be issued for each webinar you attend with us. So if you attend both of the solar programs this week, you'll get two PDFs emailed to you, one for each section. They take about 5 to 7 business days to generate, barring that we do get a quiz back from you. If you need them any sooner for licensing purposes, call into our office, or again, you can reply back to any of the emails you received, and we can help you out there as well. We'll be taking questions throughout today. On the right-hand side of your screen, there is a questions box. Anytime you have a question, either in regards to the content or for Half Moon Education, type them in there and we'll get them answered for you as soon as we can. Materials for today are in the handout section, which is below that questions box on the right-hand side of your screen. We tried to email them out earlier. Unfortunately, that didn't work due to the size limitation, so we do apologize for those of you who were expecting them earlier, but they are there. There's a blue link. When you click on that, they'll open up in your default internet browser. From there, you can either just view them or you can save them or print them. Okay, that's all I have, so let's hand everything over to Mr. J.R. Cromer. He's a master electrician with a mechanical engineering degree from the University of Pennsylvania. Thank you.
All right, thanks, Tim. And a recent qualification I picked up was residential builder. So I've passed my residential builder exam, and that just goes into kind of what I'm doing right now in Mississippi with regards to solar. And you know what is interesting about Mississippi is that it says it can't hear anything, Derek. Can some audience member kind of just test out the question or chat feature to see if you can hear me? Because I think you should be able to. So if you can't hear me, that would be something we'll fix.
I can hear you just fine, JR. If anybody else can just verify in the questions box that they can hear us, but he should be able to hear us. I'm guessing yeah, there we go. I'm guessing it's just a sound issue. You might have the wrong. I can reply via text.
All right, sounds good. Well, Mississippi has not very good solar policy, and it's not a leader in solar. However, because of that, most of the installers in Mississippi are well versed in off-grid. When I first moved to Mississippi to do some TVA kind of heavily subsidized commercial projects, I was talking with an installer, and he says, you know, it's a battery market in Mississippi. I'm like, well, that's interesting because nowhere else in the country is it like that, you know, with net metering or grid-tied solar. You know, you just plug into the grid and sell back. But to kind of throw a bone to the cooperatives and grid operators in Mississippi, there are very few customers per mile of power line in Mississippi. You know, there's more grid distribution and maintenance costs. There's less money to go around. And so they really have to take a very, you know, ultra conservative approach to solar policies such as net metering. And that can get the customer into a position where they say, well, is it even worth selling back to the grid? Should I even connect to the grid at all? And what I've discovered is that that when you get into kind of off-grid design and battery-based solar design, you really don't want to go back because in some ways it's more simple. You don't have to deal with interconnection. policies. Also, some of the components can actually get a little bit cheaper when you go off grid, not because necessarily the products are cheaper, but because they don't have all of the. Well, we'll get into that, so it'll be easier to explain that as we go along. Many of my off-grid projects, I'm working on 2 right now. One is completely off-grid. The other is kind of a weird configuration called Grid Assist that we'll talk about probably tomorrow. It's like training wheels for going off-grid. But my truly off-grid projects, the selling point, what has won me those contracts is the cost of grid expansion. So one client, a business professional, wife, 2 kids in school, not necessarily the type of person who really wanted to live off grid, but he has some acreage of land and he wanted to build about a half mile off the road, and the utility was going to charge him about $20,000 to expand the grid out to where he lives. And so there's actually rules and regulations, particularly with regulated utilities who have a monopoly to provide power in a given area, where once not just hanging a transformer on the pole and running out new service, but once you're actually getting into building raising new power lines and building the power lines out into the property, those costs can get quite expensive. So we're looking at, if you're 500 feet off the road to 2,000 feet off the road, your grid expansion costs can easily get into the tens of thousands of dollars. So that's actually, for me as a solar installer on my most recent project, it was a choice between 2 customers splitting the cost to bring power on into their properties, kind of down the property line. Well, for me, it was going to cost them $8,000 a piece. One person was building a big old house, and a year and a half from now, the other person was building a small cabin. Well, what I did instead is sold the guy building a small cabin an off-grid array, and I suspect that will result in another off-grid project from the guy building the much larger house a year and a half from now, because now he no longer has his neighbor to split the cost of grid expansion with. And so a lot of this is kind of new construction for properties that don't have power services out there, although that's not the end all. In fact, I was at a job site today doing a smart home, and we're doing a kind of a hybrid off-grid system, which is like a one-way street. So the grid can charge the battery, but the output from the system goes directly into the home and is not physically interconnected to the grid at all, other than on the input side where the battery charger is. So it's like the grid now charges a battery, and then the system supplies power to the home from the battery. We'll talk about those strategies as we move forward. But what you're looking at, overhead is cheaper than underground. I think these benchmarks are pretty good, because it's like, hey, even if you're in a rural area where like every guy and their uncle has a trencher and nobody's afraid of digging a long trench and throwing cable into the ground, well, still, there's that real cost of trenching and throwing in cable, $56 a foot. Overhead is cheaper, but then again, subject to more failure. And then, of course, if you get inside the city, your grid expansion costs can even go up, depending on if you're actually having to extend the distribution circuit rather than just hang a transformer off of it. So another aspect of solar with net metering. Net metering in the United States has traditionally been defined as you put a kilowatt hour onto the grid and they give you a retail value, or at least something near retail. Maybe not quite retail, but the spirit of it is retail. So it's a kind of, you outflow 1 kilowatt hour, you get a 1 kilowatt hour credit, provided that at the end of the month or at the end of the year, you don't zero out your bill entirely. Well, the grid operators don't really like that policy. I mean, I personally think net metering is a great policy for society. At the same time, it really does negatively impact the grid distributor. If they're getting a retail credit, they're also getting a retail credit for that grid distribution cost, and the grid distributor is seeing their revenue shrink. And so they say, now, wait a minute, my revenue's shrinking. I still have to maintain the same amount of grid. So what can I do to make up for that revenue loss? And the answer is, well, if energy is based on a metered rate, 1 kilowatt hour in, 1 kilowatt hour out, well, instead of raising the price of energy, let's just raise the fixed meter fees. So, your bill is $50 a month before you buy a dime of electricity. So there's more than one ways to skin a cat. If a grid operator is unhappy with their state mandated net metering policy, where it does exist, instead of raising their electric rates, they can just increase the fixed fees, and that kind of waters down the benefit of net metering. And so to give you an idea of where these fixed fees can become a little bit on the high end, what we see here are various rate structures. So like if you have 1 meter for an entire complex, okay, well that's more like commercial, or 3-phase time of use. Maybe you're a home machinist and you want 3-phase power into your house. Well, they're going to charge you a fixed fee that is more similar to a business or an industrial site than residential. An RV park, that might be your master meter, or it just might be that the RV park is similar to these mountaintop rate structures or these seasonal rate structures where like a hunting cabin or a fishing cabin, it might sit empty 6 months out of the year, only using $1 or $2 of electricity, even though it's very expensive to push the electricity all the way out to those remote rural areas. That's where you start to see the bill be more of a fixed fee rather than a metered electrical rate. All right, good. Most people can hear in class, so that will make the class all the more worthwhile. So what I wanted to do next was to say, okay, well, aside from these kind of weird rate structures that are special use cases, where in the U.S. are fixed fees high without it being special, with it just being, this is your residential electric bill and the fixed fee is this much of it? And I was kind of surprised by the results. I mean, this isn't New York City. This isn't California. It's the middle of the country. It's Indiana and Illinois, Ohio, Virginia, and almost uniformly they're cooperatives rather than investor-owned utilities or municipalities. And so it's really where I see a big off-grid market opportunity is in these cooperatives. Oftentimes the cooperatives are exempted from their state net metering laws. So cooperatives have been viewed as buying groups rather than generators. And so They, whether it be an environmental policy or what have you, they say let's regulate the generators, let's regulate the investor-owned utilities, but presumably the cooperatives are just buying groups that are comprised of all their individual members acting in their own self-interest. So let's just let them kind of set their own rates and billing structures. And also, cooperatives will tend to have higher distribution and maintenance costs. And so we see these cooperatives kind of moving towards ever increasing fixed fees as a way to, make sure that they have enough money to maintain their monopoly. And so this is what solar looks like in Mississippi on these electric cooperative grids. The retail price of electricity works out to be about 12 cents a kilowatt hour. It's actually in Mississippi, it's 12 cents a kilowatt hour total, but then when you back out the fixed meter fee, it's only about 9 cents a kilowatt hour. And so even if we had net metering in Mississippi, we wouldn't get a retail 12-cent rate. We'd only get a 9-cent rate, which is 25% less than retail. But actually in Mississippi, the buyback rate on our cooperatives it's a little bit less than 3 cents a kilowatt hour. And the problem with solar, especially solar where you want to knock out 100% of your electric bill. And hey, most solar customers, they want to knock out 100% of your electric bill. Larger projects are a lot cheaper per unit pricing than smaller projects. And so, I recently did a 2 pallets of solar, which is 14 kilowatts for a residential site. And I gave the customer around a $2 a watt installation price. We really have to do soul searching with our installation prices in Mississippi. Otherwise, the economics just don't work at all. If I had done a 7 kilowatt array instead of a 14 kilowatt array, I would have bid a $3 a watt installation price. And so by doubling the project size, I can give them a unit price discount of about 33%. And so it is even at the residential level, economies of scale, doing larger projects, trying to hit that 100% offset mark is going to be a way to lower the installation per watt price of the project. But then you get this problem, which is if I have a very large array, and I'm trying to produce 100% of my facility power, well, that power only comes when the sun is up. And so if I'm offsetting 100% of my power, that means 2/3 of my solar production is going to not be in line with my consumption, but either needs to be sold to the grid and then compensated or stored in a battery. Otherwise, it's just wasted, which, traditional power plants do have this concept of stranded electricity when they are producing, but they don't have any off-takers for the electricity, and, it costs them money as well. Even if you just did a small array, you'd have to have a teeny, tiny array not to produce outflow onto the grid in a batteryless system. So, if instead of doing a 7 kilowatt array for $3 a watt, I could have done a 3 kilowatt array for maybe $4.50 a watt. And that way his generation rate would be closer to 9 to 12 cents, but the installation price upticks to the point where he doesn't get a good return on investment. Not taking into account the asset value of solar or anything like that, just simple economic payback. Smaller arrays might have less outflow, and that might improve the generation rate, but larger arrays are cheaper to install. So where's that happy medium? And so like even a small solar array will produce outflow. And you know, in the winter time, you know, maybe your solar production is down and you can run off electrical heat during the day. And so I'll often tell my batteryless customers in Mississippi, you know, hey, go get electric space heaters and put them on timers so that you're running them just during the day and then use your gas heat for the rest of your time, because you got to put that stranded electricity to work. You know, in the summertime, you know, maybe your solar production is more coinciding with your heavy air conditioning electrical use. But even if you had a perfectly sized system, and these are not large systems, but even if you had a perfectly sized system where, you know, let's say your home is averaging 6 kilowatts of power in the summer and, you know, 3 kilowatts of power in the winter, and so you go and you do a 6 kilowatt array to not really produce much outflow, and then it declines in winter. Well, you still have spring and fall when your electric use is down and your solar production is up, because you get these bright, clear, springtime, cold days where it's still sunny outside. And so even a small solar array can produce outflow onto the grid. So if you don't have good outflow policy, that is a way to stymie residential or consumer-owned solar in your market. And then you get to, well, okay, well, what if I put the energy into a battery? So instead of outflowing onto the grid, you store it in a battery and you deploy that energy when you need it. This is actually a very cost-effective method in the commercial market. And we teach a class with Half Moon called Commercial Solar Peakers, where, you know, we talk about the economics of generating a very small amount of solar power, storing it all in a battery, and only using that battery during peak times to reduce the demand charge of a building. That's the most cost-effective application of solar. That market's growing by triple-digit growth rates right now. It's a market that a lot of people don't even realize exists. It's kind of that brand new. But that's for commercial customers with a very specialized billing structure that allows them to take advantage of demand savings. Most residential customers are not on demand charge rate structures. So what about the concept of, hey, I have a time of use rate structure where I have a high peak rate and a low off peak rate. And in the past, the peak rates have been during the day, but now most companies are pushing those peak rates on into the evening. And that's not to say that the problem is we have peak demand in the evening and not in the middle of the day. It's that if you incentivize peak demand during the day, people buy solar, and then you no longer have that demand issue in the middle of the day. In fact, you have a little bit more of a problem, which is how to ramp up very quickly from a off peak to a peak time. Anyway, what if your power company does give you a time of use rate structure that says, all right, well, let's just you know, even forget solar for a minute. What if we just plugged a battery into our electric service panel and charged it during off-peak times and discharged it during peak times? And so you look at your time of use rate structures, and you can get differentials of 7 or 8 cents a kilowatt hour or more during that time. So can you day trade electricity with your solar battery? And the answer is it's kind of tough to do that. And the reason is, let's just look at Mississippi, for example. This should probably be a 0 right here for 3 cents. You know, let's assume that I get a 12-cent credit for my peak rate and a 3-cent credit for my off-peak rate. Or in other words, as this relates to solar, let's assume my electric rate is 12 cents, but the buyback is only 3 cents. And so I have about a 9-cent differential between peak and off peak. Well, the problem is batteries cost money to use. You take the upfront cost of buying and installing a battery and you divide it by how many kilowatt hours can go in and then out of that battery over its total life, and you get to around a 10 cent a kilowatt hour cost of running the battery. So even if I have a time of use rate of 9 cents between peak and off peak, if it costs me 10 cents to use the battery, I'm actually losing money by day trading my electricity. Even though I have a lower electric bill, I have spent more money on batteries than what I've saved off my electric bill. Now, I know solar customers who do that because they want the battery and they don't want to spend any money on their electric bill. And I would call that a spiteful battery. And maybe solar customers in areas where they get kind of a raw deal on their solar buyback, maybe they do feel slighted and want to get a spiteful battery. But at that point, I would rather just say, well, why don't you consider off grid rather than keeping your grid connection, especially when you start looking at the meter fees getting into the $30 to $50 a month. Okay, so say in my market in Mississippi, to make solar cheap, I usually will force my customers to buy by the pallet. And so I really just do like 7 kilowatt or 14 kilowatt or 21 kilowatt projects, because that's a 1 pallet, 2 pallets, 3 pallets. And I get my designs to the point where it's like, okay, I know which inverter I need for my small, medium, or large configuration, and just kind of fit that to the customer rather than giving them something that's a little bit more customized, just to reduce the design, development, shipping fees, trying to apply to like optimize everything about the project to get the project to the point where it has a reasonable payback in an area where solar does not have a very good payback. So, we look at things like, okay, the inverter cost, a Solar Edge 3 kilowatt inverter costs $1,000, but a 10 kilowatt inverter costs $2,400. And so I spend 2.5 times as much on my inverter, but I get over 3 times as much inverter capacity. That's the economies of scale that we're talking about. And so like a 5 kilowatt array at $4 a watt versus a 20 kilowatt array at $2 a watt, we're talking about the difference between a $20,000 project and a $40,000 project, but the more expensive project, you get a whole lot more solar. But then again, there's that whole outflow rate. Whereas if I do a 5 kilowatt project, it will not produce much outflow onto the grid, whereas a 20 kilowatt would. And so that kind of gets you into kind of a sweet spot where generally in Mississippi, if I'm doing a batteryless array, it's just going to be a 7 kilowatt system. The customer who got a 14 kilowatt was not on a co-op. He was on Entergy, and Entergy has a buyback rate of 7 cents instead of 2.5. And so, that's why we went with a little bit larger of an array for that particular customer. Now, fixed fees are increasing And there's kind of a hidden cost to a solar customer when you have high fixed fees and a low energy rate. Well, even if you don't have like, okay, a low energy use structure, a mid energy use structure, a high energy structure, if you just had one rate for everyone, every residential household in a territory. And so let's just assume for a moment that rate's going to be a $20 a month meter fee and a 12 cent a kilowatt hour energy rate. Okay, so let's look at a household that uses 500 kilowatt hours a month. This might be a solar household. You know, they've reduced their electric bill. They're only buying 500 kilowatt hours from the utility. It could also be a low-income household of retirees who don't turn the air conditioning on until they go to sleep because they're on a fixed budget and they're really trying to control their electric bill. Or you go all the way up to a larger home that is inefficient and uses a lot of electricity. Okay. So we take the 12 cent a kilowatt hour rate and we multiply it by how many kilowatt hours they use, and then we add that to the meter fee, and then we go back and divide the total by how many kilowatt hours they use. And what we find is that homes that use less electricity from the grid, even if it's a flat rate structure, homes that use less electricity from the grid effectively are paying a higher rate per kilowatt hour delivered than the homes that use more energy from the grid. And so at that point, it's like, well, if you already have solar, or if you have just a small home that's energy efficient and you only use a little bit of electricity, those customers, it will be more cost effective to get them to go off grid than a higher energy use home that might need a larger battery for less total effective savings. In other words, that $20 a month charge is a better deal for a high energy use home than it is for a low energy use home. And that's kind of interesting because everyone talks about, well, how do we get solar onto low income households or fixed income households? And it's like, well, maybe if the home is small enough, that's actually a better target for taking off grid than a larger home, where the being grid connected is a little bit better deal. Then again, usually it's the larger homes where the customers have the money to do a project. So then there's additional fees and charges that are added on to the bill as part of the solar interconnection process or after you've been interconnected. So not only do you have wait times for interconnections, and some utilities across the country have been saying, hey, we are so inundated with solar interconnection applications that we cannot even meet our required guidelines of approving the interconnection. And that can get kind of lame if you're doing the project and you have to wait for a month before the utility gets back to you and says, okay, you can do solar. I would like to see solar be treated more like just pulling an electrical permit. But if you're not interconnecting to the grid at all, you don't have to deal with the interconnection application process or the associated fees involved. Now, some utilities are trying to have their cake and eat it too. They say, hey, look, if your solar array is connected to your home wiring, it is connected to our power grid. And that's not a true statement, because I can do a solar array that's connected to a home wiring that is physically, not software controls, but physically incapable of backfeeding onto Mississippi Power's grid, they still might come around and try and charge you special fees for having a solar array on your property. Now, I haven't encountered that thus far. I have an interesting project, this one I'm working on now, where that will kind of be a test run of that. But generally, what will happen is the utilities will charge you to install a digital meter on the home. Even if you already have a digital meter on the home, they'll charge you to install a different digital meter, and that is capable of reading the inflow and the outflow independently of each other. And then in some states like Mississippi, they will charge you an additional meter fee because you have that special meter. And all of that is associated with outflowing onto the grid. They say, well, if we're compensating you for the outflow, we need a little bit more revenue to account for that process. Whether you agree with that or not, that's how it is. Now, in fact, the whole Tennessee Valley Authority region, in their 2018 rate change report, on page 1 of the executive summary, they say our energy pricing over incentivizes consumer-owned distributed energy resources, solar. They say the TVA's program over incentivizes consumer installed solar. Now, keep in mind, the TVA says the cooperatives only need to buy back the solar outflow at 2.5 cents a kilowatt hour, and that they're entitled to charge additional fees onto that solar customer. And even so, they say, and that is over incentivizing consumer-owned solar because they don't need new energy projects in the TVA region. And so if you have more supply than demand, and then the supply continues to increase, they say somehow that raises electricity prices. You know, I don't know. I don't think that is a well thought out argument, but that is what they say. So there's, the reason why this is on the slide is just to show you, in fact, while renewable energy is expanding throughout the United States, the solar policies are increasing the costs of grid participation onto the customer, and that trend is spreading. So the TVA program, it's called Buy All, Sell All, and either you're forced to sell all of the electricity on a standalone connection to the TVA at something like 60% of retail, or if you want to tie the solar array into your home, the buyback rate is only like 20% of retail. That contract structure just the past year has spread to Connecticut, notably, and it's in Georgia and other kind of regulated utility monopoly states. Kind of ironically, in Houston, Texas, there is no net metering mandate, and they have a deregulated grid, and the customers in Houston, Texas get better buyback rates when there's competition for that solar customer than Mississippi customers get on a regulated monopoly. So the regulated monopoly is not serving the solar customers very well. And so what I want to show you is the most extreme example that I came across, which is electric cooperative in Mississippi, where the solar meter fee is $15 a month, and then they subtract additionally almost a penny and a half off of the buyback rate for wheeling or management or whatever. So it's not only a fixed meter fee, but it's a production-based fee on top of that. And so this cooperative's buyback rate is, they're not a TVA cooperative. So non-TVA cooperatives are buying back at 4.5 cents. Well, they say, well, actually, we're going to subtract 1.5 cents out of that. We're going to charge you an additional $15 a month. And so if you run the math and you say, okay, well, how many kilowatt hours outflowed at 3 cents a kilowatt hour do I need in order to offset $15 a month? The answer is 477 kilowatt hours. And so, okay, well, how large of an array do I need to generate 477 kilowatt hours? And long story short, that's about a 4 kilowatt array. And so on Coastal Electric, the way their policy plays out is you have to buy an additional 4 kilowatts of solar in order to overcome the cost of participating in any sort of buyback. So, it's really just wholly uneconomic to do it this way. And so what I would prefer is to not play that game when you're in a market where the utility policy is so punitive, but instead to reconsider off-grid. Another argument against solar that I hear made at the public utility level is that solar is unreliable. And it really bothers me because it's like, I know when the power goes out, my off-grid customers are doing just fine, which is the opposite of unreliability. In fact, it is improved reliability. So, you look at what causes power failures. This has played out in a discussion between underground and above ground power lines. And so what we see is there's a couple of graphs here. The system average interruption duration index. And so this tan line is overhead, and then this blue line is overhead transmission lines. And what we can see is overhead power, when it goes out, it system average interruption duration. So it goes out for a while. These are slightly different graphs. This one is the frequency. So how frequently does the power go out compared for overhead lines or underground lines? And we conclude that underground lines are more reliable power than overhead. But as we saw a few slides earlier, it also costs more. And so there's this trade-off we do on, do we want more reliable electricity or do we want more costly electricity? And that gets into, do you want like overhead lines or underground lines? Well, I would look at an off-grid solar array as costing even more than that, but also being even more reliable. And so it really irks me to hear public utility commissioners say, well, I guess you could go off grid, but what'll you do at night when you run out of electricity? Because it's like, no, actually, if you have solar on your rooftop and the power lines go straight through the roof down to a battery below, there's no trees to knock it out. That would at least have the same reliability as underground wiring, if not more. And so that argument that solar is unreliable kind of goes away as batteries come into the system. And so another question is, well, can't you just have solar and batteries but still keep your grid connection? Do you have to go off grid with a solar battery? And I would say that the problem that I see most people overlooking is that the most popular storage options on the residential market, like the Tesla Powerwall, or in the solar industry, there's a very popular system called Solar Edge, which puts little boxes on the roof to optimize the power. And then it's not a DC to AC inversion up on the roof. It's DC to DC. And so they take a DC bus back down to the inverter and use it to charge a lithium ion battery. And so you have your solar, you have your battery. These are grid connected inverters, so you can still outflow to the grid and sell back. Maybe you have net metering and you get a good rate for that. If you don't have net metering, you can use the lithium ion battery to kind of keep your energy. As we learned earlier, the economics are kind of where you're just spinning your wheels. You're spending money on batteries. You're not spending money on your electric bill so much, but it's a wash on whether or not that's economic. But the customer really wants the battery because if the power goes out, they want to use their solar array. So, imagine Hurricane Sandy. New Jersey has subsidized the heck out of their solar industry through their SREC program. So there's plenty of customers with solar on their house in New Jersey before Sandy. And Sandy hits and it wipes out the grid. And none of these solar array owners can use their array during a blackout because they didn't get batteries put in. And so then they go and run out and say, well, I'm not going through that again. Let me add some batteries to my solar array. And the problem is the solar battery options for these grid-tied inverters will, when the power goes out, it'll isolate a critical load and feed the critical load panel with the battery. And so there's costs associated with rewiring your service panel, which is just doing rework. It's not adding new stuff to your home. It's not whole house power. It's just powering a few things. And then, maybe this is the southerner in me, but when the power goes out, the thing that I want to keep going is the air conditioner, and these critical load panels from the Tesla Powerwall and from Solar Edge. They are not powerful enough to run a central air conditioning unit. They could do a 120 volt window unit, but they can't take the central air condition. And so that's the problem that I have with a lot of the grid-tied inverters, which rely on the critical load to isolate the solar array and critical load from the grid during a power failure, is that their critical load output capacity is simply not very much. On top of that, depending on how you wire the system, whether or not you're wiring the solar array directly into the batteries or having one battery inverter right next to a non-battery inverter, it might be that when the power goes out, you only have the battery, but the solar array goes out too, depending on how you wire it, depending on your material selection, product selection. And so the short of it is a lot of grid-tied batteries, they're not very useful for providing backup power during emergency, except for a very small critical load panel. They're not whole house solutions. And I don't know, I find that dissatisfactory. And so here in this graphic, we're showing the grid is out. Your solar battery-free inverter has turned off. And then your battery inverter that's in parallel is protecting your critical loads, but not your air conditioner. Now, this is where we get into kind of hacking the solar array to do things with it that maybe the manufacturer doesn't want you to do. Because really, what's happening here is this inverter, this batteryless solar array. So let's say you already have solar on your home and you're thinking of doing a retrofit, and so the easiest solution would be just to buy a battery inverter and wire it in parallel with your service panel. But now it's protecting critical loads. And the thing is, your batteryless inverter, it needs to see power to turn on because of its grid-tied protection. So the inverters have protections built into them so that if the grid goes out, the inverter turns off. That's because if a tree falls over a power line, they don't want the distributed solar inverters backfeeding the grid and executing the linemen who are trying to repair the power lines. And so a safety provision is built into their listing that says, okay, whenever they see a grid signal, it'll take the inverter 5 minutes to turn on so that the linemen and repairmen, can get their work done in a safe and effective manner. Okay, but what if I wanted to use my solar array during an emergency and I had a battery inverter that was capable of outputting 240 volts? Could I trick my solar array into turning on? And the answer is yes. You can turn a solar array on with a generator. You can turn a solar array on with a parallel battery inverter. The only issue is, well, how do I actually do that and maintain my grid connected safety procedure or safety rate listing? And the answer is there's a term called a generator interlock switch, which is a device that was used to land a just regular gas generator at the top of the bus bar. So in past solar classes, we talk about interconnecting solar at the bottom of the bus bar, but this generator interlock switch would go at the top of the bus bar, and that's because they install a physical plate around where the generator lands and where the main is, so that only one of these two can be on at the same time. So right now, this disconnect is on and this disconnect is off. And then if we took this plate and adjusted it, it would slide over and slide over. And so this could be on while this would be off. So it's a physical plate that, and you see these kind of safety screws bolted into it. It makes it so that you either have to have your main turned on and your generator turned off, or your main turned off and your generator turned on. Okay, well, here is the critical load panel for one of the most popular grid-tied storage solutions, which is SolarEdge. And what we can see with SolarEdge is they're outputting a leg 1, leg 2, and neutral. That's a 240 volt split phase service coming out of this SolarEdge critical load panel. And so what you could do, let's say you were this past customer and what you currently have is just solar and a SolarEdge inverter, and that's it. And then you say, okay, well, I want to go and add a battery inverter. And in this case, we're using a different SolarEdge inverter. And so we have two systems here, two inverters. instead of wiring the output of this inverter to a critical load panel, you could install an interlock switch and wire the critical load panel to the top of your service panel. And what that would do is it would show any, if you had a solar inverter landed on the panel here that was a batteryless inverter, this is off, this turns on, and it turns your solar array on. And that way you have your solar array working and your battery working. Although this is not compliant with the intended use of these critical load panels. And so you kind of get out of your warranty for that. And so, grid-tied solar with backup batteries for power outages is a little bit less satisfactory than you would think. The storage inverter goes up to 7 kilowatts, and that can only get about half your power. The critical load panel is even smaller than that. There is an inverter called SMA that makes a dedicated power outlet that will turn on during the day without batteries and just run off the solar array, but they substantially curtail the amount of power you can get out of that. It's only about 2 kilowatts. And then on top of that, these grid-tied battery inverters are the most expensive inverter on the market, because not only do they have to take the power from the solar array and squirt it out onto the grid, but now they need to take power from the grid and suck it into the battery. So it's two directions, not just one: solar out and then grid in to charge the battery. And then they have to have all the listings, and then you have to have all the critical load infrastructure on top of that for something that can only protect critical loads and not really power the entire house, unless you trick the system into allowing you to use the critical load power and your solar array power at the same time. But that's going to void your warranty. And so it's not only a not satisfactory solution, it's also a very expensive solution. Okay, one thing that's interesting about these grid-tied battery systems is they all seem to be focused on lithium ion. So you have the Tesla Powerwall, that's lithium ion. You have the Solar Edge solution, that's lithium ion. LG Chem is lithium ion. Everyone's talking about lithium ion, lithium ion, lithium ion. Whereas you get into the off-grid arena, and all of a sudden people are talking about lead acid batteries, 24-volt battery banks, 48-volt battery banks. But the lithium ion battery banks are designed to be around high voltage and low amperage. And the real problem with lead acid is that it's designed to be kind of lower voltage and higher amperage. It's not that you can't get high voltage out of it, but you still will have the high amperage along for the ride. And power equals volts times amps. And so if you did a high voltage lead acid battery bank, it would just be a way powerful industrial grade battery bank. The fact is, this is one of my favorite product lines for lead acid. And here's a 12-volt battery, and let's go down to their super powerful 1000 amp battery. And so what we're talking about here is a volt times an amp is a watt. So 1,160 amps times 12 volts. That's a 14 kilowatt hour battery. And by the time I get it up to 48 volts, that would be times 4. what you get is you go from a 14 kilowatt battery to a 55 kilowatt hour battery, and that's just at 48 volts. So if you went all the way up to the high voltage ratings of lithium ion with your lead acid batteries, you would be getting into 1,000 kilowatt hour, 2,000 kilowatt hour battery banks, which are too large and too expensive for home use. And so the kind of the most popular eye-catching Tesla Powerwall SolarEdge battery systems are based on high voltage batteries, and that means they can't really use lead acid. They're really designed to be around lithium ion. And the thing is, lithium ion is very expensive, and so lithium ion tends to be high voltage and low amperage. And so it's these batteries that can only output 40 amp hours rather than 1,000 amp hours. Look at the difference between that. The lithium ion Tesla Powerwall solution outputs 40 amp hours. Lead acid can output 1,000 amp hours. It's what it is the lithium ion batteries at the residential level are not capable of outputting that much power. And so they limit them to these 2 kilowatt or 3 kilowatt critical load panel infrastructure. If you wired it up to a central air conditioning unit, the storage capacity would be so small for their kind of entry-level products that it would just zap all the power out of the battery bank. And so that can kind of trip you up a little bit cost-wise, given that you're not just buying the lithium-ion battery, you're buying all the hardware that you need to get the lithium-ion battery to work. And all of these battery inverters, too, are on their first generation or second iteration product line, so they're not very good. In fact, I'm ready for SolarEdge to iterate their battery inverter design. I'm not very impressed with it. So kind of in short, grid-tied batteries, grid-tied solar inverters are more about lowering your electric bill rather than providing backup power. And while that can be a very cost-effective application at the commercial level, at the residential level, it kind of turns out to be where you're just spinning your wheels and you're buying batteries instead of paying your electric bill, but you're really not saving any money. On top of that, power companies do not want solar customers on their grid and will rig the rate structures against the solar customer. The grid is less reliable than an off-grid array. And it's kind of like the solar industry back in 2008, except now it's the solar plus battery industry in 2018. The one thing that is kind of lacking is long-term financing. Whereas if we could get long-term financing for this off-grid market, it'll really start to pick up a notch. Actually, right now, there are companies providing not bank loans for this stuff, but unconventional loans at 0.5% above what you would get at a bank for a home improvement loan for 20 years. So the private financing is picking up a notch. And so in conclusion, going off grid is expensive, but if you look at what you want, which is whole house backup power, and you look at the cost of the grid tied components, and then especially if you look at if you're facing either high meter fees or costly grid expansion fees, there are niche markets where going off grid can actually be the most economic option for solar ownership. And so, that's where you get into this kind of new thing going on in the industry. It's not new, it's just new in volume, that the utility has used solar unfriendly policies to stymie the growth in solar, but instead it has cultivated a market where the installers develop the expertise to take the customers off grid. So let's learn how to do that. So one of the kind of harder things to do, I guess, is to say, well, how large of a solar array do I need? How large of a battery bank do I need? And often you will only have the 12-month electrical history of the client. If you had their 15-minute by 15-minute interval data, such as most businesses have because they're billed for their maximum 15-minute demand, so they might get a report that has every 15-minute increment of their building's energy use spelled out for the entire year. And that data is very useful for right-sizing the system. But often, residential customers don't have this data. So how do you size a system based on a 12-month electrical billing history? This is Aurora Solar. What they've done is developed a little load profile tool where you input your 12-month billing history, and then you complete a survey. Do you have a pool? Do you have an electric vehicle? Do you have air conditioning? Do you have electric heating? Do you have an electric hot water heater? And then based on your region and based on the list of appliances you give it, it will guess at your electrical load profile based on whatever information's in their database. It's not a perfect guess, but it's close, and it's better than nothing. And so what we see in these graphics is, okay, in the summertime, we see high electrical load, particularly in the afternoon and into the evening. In the wintertime, our air conditioning goes away, and we have a lot of electric heat, not so much in the middle of the day when it's sunny, but definitely in the morning. So actually, these are kind of generalizations that just kind of, in the springtime, you kind of have a mix. You might have the heat in the morning and air conditioning in the afternoon, Okay. What I think is a little bit more useful is just understanding what your average or sustained electric load should be. Not that it is, but what it could be, what's reasonable for an electric load. And what we see is in this particular house, in, say, the wintertime, when they have most of their electric bill, it's mostly home heat. And they're averaging, let's just be conservative, this is an 8. This particular customer's bill, they're averaging, a maximum draw of 8 kilowatts and then kind of a sustained draw. Maybe we look at a 30-minute window or maybe a 1-hour window at around 7 kilowatts, and they're mostly below that. And so I say, okay, well, I need a inverter that is capable of delivering, 8 kilowatts of power to this client. The one thing that can make these assumptions really bad is tankless water heaters. Anything that uses electrical heating uses a lot of electricity. And it's not so much that electric heating is bad for solar. If you have enough electricity available, fine. Motor loads, compressor loads, those are harder on a battery and on a solar array than using electricity to generate heat. It's just that using electricity to generate heat uses a lot of electricity. But tankless water heaters that surge, tankless water heaters are rated for 20 kilowatts. And so if you do not have a 20 kilowatt surge capacity on your inverter, then you may not be able to have a tankless water heater. It would be a lot better to have a tank and have that tank be a low power level throughout the day rather than have a surge. And so kind of the goal in off-grid design is when you're picking your appliances, try and have this load profile be as flat as possible. Or if you're wanting to go the next step, to have a intelligent smart home that can kind of surge up and down with your solar array production. So Todd asks, okay, who does these graphics? This is a solar design software, Aurora. And then the other one that does stuff like this that is just as good. In fact, for commercial modeling, it's a little bit better. For economic modeling, it's a little bit better, is called Energy Toolbase. We talk about them in other classes. Aurora is more of a solar design tool where you design the whole solar array. Energy Toolbase is more of an economic modeler, and they both kind of meet in the middle when it comes to this stuff. I really only think this stuff is useful as a sanity check to make sure that your inverter is going to be able to output enough power. And so what I would do instead is log into my electrical account with my power company and see if they're providing the 15-minute interval data available as a download. And if they're not, like when I did my very first off-grid design, I just did a comparative analysis of the home I was designing to interval data that I had for a home that was in Oklahoma that had a little bit harsher environment than Mississippi, equivalent sized homes, similar appliances, and just based it off a standard load profile. But it's not that when you live off grid, you have to be energy impoverished. The thing about with solar, we saw those graphs earlier, you have a ton of power in the middle of the day and then not a lot of power elsewhere, or everywhere else you're running off batteries. And so actually in the very middle of the day, you have as much electricity as you can possibly use. And so that throws into question a lot of assumptions about off-grid living, like, do I need an energy efficient freezer? Or can I have a deep freeze? Do I just need a small refrigerator? Well, yeah, you could actually have, not just one deep freeze, but two. And then take the bottom of the deep freeze and put in bricks. Just put bricks in the bottom of your deep freeze and put some thermal mass into that deep freeze. And so now you have half the volume, but you have two of them. And then you put them on a timer so that they only turn on during the day, and then they coast off their thermal mass the rest of the time. Instead of having one refrigerator, maybe you have a refrigerator that's smaller that you use for the day, and then a refrigerator for storage that you're not opening and shutting all the time. It's like, well, okay, well, maybe you use wood chip heating, but it's not like in the winter you're going to have to use that wood chip heating every single day. It's during the day you're running off electric heat, and then if you need any more heat, you can use your wood chip heater. So, you can have a swimming pool, a hot tub, all of these major appliances, or even a tankless water heater if you're right size appropriately. But we do have to be more intelligent about how we're using our appliances. And so I kind of get into, when you're going off grid, it's not that you have to go away from electrical devices and into gas and into other forms of power and heat. It's that you have to figure out how to do smart load shifting so you can take advantage of that daytime electricity without cycling your batteries. All right, so back to figuring out how large of an array we need. Here is the month-to-month electric use that we're trying to design around. So a little bit different than the previous bill we saw, but what we see here is higher energy use in the winter, a dip in the spring and fall, peak energy use in the middle of summer, a dip in fall, and then it picks back up in the winter time. And if I looked at this energy use and said, well, what size of solar do I need to not outflow onto the grid? That might be a 4 kilowatt array. Or if I had an annual net metering plan, I would sum up the total of all this energy and say, how large of an array do I need to produce 17,000 kilowatt hours of electricity a year? And my annual offset, the array would be 12.5 kilowatts. Or if I didn't have annual net metering, but I had month-to-month net metering, I might be looking to offset not my annual consumption, but to say, okay, I'm going to do a large enough array to offset March and April. And then I have a little bit of electric bill in summer and winter. One key difference with off-grid is you're not caring about March and April. You're not caring about October, November, and the fall. What you really want to look at is peak use in the summertime and peak use in the wintertime, because you want to make sure you don't run out of electricity. You want to make sure you have enough production in the summer and in the winter to fill those batteries back up. Now, this is not the end of the process. This is just to hone in on what system size we need, because we have to remember in the winter and in the summer, you could go multiple days in a row without the sun coming out. Or you could go multiple days in a row where the sun does come out, and then your batteries get all the way full, and some of that electricity gets wasted. And certainly in March and April, in October and November, we're going to have a lot of electricity that's wasted. And so that's where I say, don't think about off-grid as being energy poverty, because there's going to be times when you have energy overabundance, even for a well-sized rather than oversized system. This is just to have us kind of hone in on what size of system we need. And so what we do is we take our consumption figures and then we go and run a PV watts calculation and kind of match up January and August and September. So let's see here. Okay, so I'm just going to do a real quick PV watts calculation for my area. So I'll put it into the link. You can do it for your area. Hold on, let me put it into the chat. So I'm going, and right now I'm in Tupelo, Mississippi. I work all over Mississippi. Right now I'm doing a project up in North Mississippi. So PV watts is a very easy to use calculator. I don't recommend changing too much. One thing I do recommend is running a PV watts calculation for 1 kilowatt, because in our model we'll use that as a scalar. A 5 kilowatt array will produce 5 times as much as a 1 kilowatt. And I don't really recommend changing anything else. This will give you conservative figures. One thing you might change is the tilt and azimuth of the array. And later tomorrow we'll talk about tracking arrays, and PV watts can model tracking. And so we're going to do a roof mount, tilted up, line of latitude, and you can explore what goes into the PV watts calculation on your own. But what we see is, just very quickly using PV watts, we get a month-by-month printout of what a typical year is going to do. Now, not all years are typical, so it does, behoove you to err on the side of oversizing for off-grid. And so what I would look at this system, I'd say, okay, they need a 18 kilowatt system, and it's about 7 kilowatts in a pallet. 14 would be too small. They're going to do a 3 pallet system, and it'll be a 20 kilowatt, 21 kilowatt solar array. That'll be err on the side of being conservative. So we still have to go and figure out how to go from our solar array size and our consumption into our battery bank size. We're not there yet, but we're going to bring this data in to it. And just the thing that I think is worth pointing out is, let's say you got 4 kilowatts at $3.50 a watt, and then you got a 20 kilowatt array at $2 a watt. We just talked about that earlier, but if you have the space on your roof, if you have the space on the ground, a pallet of solar panels costs around $4,000. And so it's the cost of the battery, the labor, the equipment rental, the service panel work, the design work, the mobilization, getting the guys to site, ordering the material. That's where your cost is. Just adding one more pallet of panels and putting on 25 additional panels is not going to make or break the bank like it used to. When I got into the solar industry back in 2008, solar panels cost over $3 a watt just for the panel. And typically I'm buying around 40 cents a watt because I go bargain bin hunting. I don't have a lot of respect for high quality panels. I mean, the term you get what you pay for is not as applicable to solar panels. I mean, generally, if you're in a high priced electricity market, if you have a high priced real estate market, that's when you go for a top shelf panel. When you buy a more expensive solar panel, you're really buying space efficiency. You're buying a smaller footprint. So in Mississippi, we don't need the smaller footprint. We have the one thing about Mississippi is the rooftops are very plain and boring. And that means you can fit a whole bunch of rectangles on them. We don't have all this staggered roof lines that you see in other places. So, it's very easy to fit quite a large solar array on top of a garage or a barn or a basic roof plane. So one of the design constraints we need to figure out is how many days in a row we're going to go without sun. Well, actually, PV Watts tells us this. So one of my favorite features of PV Watts, everyone forgets it, but once you get to this kind of end screen for PV Watts, you can scroll all the way down to the bottom and download the hourly performance data of PV Watts. And what that's going to do is get you an hour by hour estimate of what your solar production is going to be based off local weather data. And so here we have our PV Watts. Let me try and make it a little bit more friendly to see. So here we are in Tupelo, Mississippi, and here's our PV Watts data. And for every hour of the day, every day of the year, from January 1st all the way down to December 31st, we have all this data. We have the beam irradiance. We have diffuse irradiance. We have the temperature of the solar array, which sometimes that's kind of interesting to figure out. Sometimes it can be very useful to know how hot the panels get up on the rooftop or how cold the panels get. So finally, what PV Watts is doing is it's taking the beam irradiance and diffuse irradiance and getting us to the total irradiance on the solar panel. And what we can see is it's distinguishing between sunny beam irradiance and cloudy diffuse irradiance. And so on January 1st, it's kind of like half and half. On January 2nd, we have a lot more direct irradiance and a lot less diffuse irradiance. On January 3rd, same thing. It's a sunny day. January 4th, it's a sunny day. January 5th, it's a sunny day. 6th, it's a sunny day. Uh-oh. Here's January 7th, and it's a cloudy day. And so what we can do is just chart for every single day of the year how much irradiance the solar array is going to get. Now, all of that's you don't actually have to chart that because all of that is going to be taken into consideration when you get to the final number, which is the system output measured in watts. And so what I'll do is I'll just take that number and divide it by 1,000. So I'll get my output in kilowatts. And of course, because this is for every hour of the day, what I know is that on January 1st at noon, my system is producing 0.26 kilowatts. It's producing 0.26 kilowatts for 1 hour. It's producing 0.26 kilowatt hours. And those were on those cloudy days. This is for a 1 kilowatt array. And so actually, what I'll do is I'll put another system cell here. Let's say we were going with a 21 kilowatt array. Now you have to know a little bit of spreadsheet technique to build your own model. But now, because I did this calculation for a 1 kilowatt array, I'm just multiplying this column by my system size, and now I can easily adjust my data and say, what if I do a 14 kilowatt array? What if I do a 10 kilowatt array? My figures adjust. And so now I know what my system output is. This is my system output in kilowatts. It's also broken into 1 hour bars. And so now I know how much my solar array is producing in kilowatt hours for various sizes. Great. The next thing I'm going to do, and we'll take a break in a minute or so. I think, unless this is the 7-hour program. Hold on 1 second. This is going to 2:15 and the 2:15. Yeah, so we're coming up on our break. But before we lose this line of thought, let's go through the process, and then we'll take a break, and then we'll pick it up right back after that. So what I'm going to do is I'm going to get my system output for every single hour of the day. And you can explore overcast performance versus sunny performance. There's a lot of analytics you can get out of this, and one of them is that solar will produce on overcast days. It's just there's a big difference between a lightly overcast day and duck soup. And so actually not all overcast days are bad. In fact, if you oversize the array, then you might find that even on overcast days, you're not draining your battery bank. So, you definitely want to err on the side of oversizing the PV array, particularly if you're in cloudy areas or cloudy winter. So, for example, this is me charting out the solar production, and what I can see is that if I go through this 4-day period without sun, well, by doubling the size of the solar array, maybe this day is more like a regular day, and this day is not so bad, and so I only go a shorter period of time for when I'm really drawing down on my battery bank. And so, maybe there's a point where you say, okay, well, most days of the month in my off-grid, Like if it's a luxury off grid, most days of my month, I'm just always filling my battery back up and I don't have to care at all about energy efficiency. And then I'm oversizing so that on overcast days, I still produce a lot of power. It's just on the hurricane or the blizzard when I'm not producing power. And so that begs a question of, does efficiency really matter in off-grid design, which is kind of a heretical thought, but just keep in mind that on a well-sized solar system, you're going to have most days, the goal is to charge the battery all the way back up to the top. And so once you get to that finish line, then you have stranded electricity, then you have surplus electricity. And so, if you say have a bunch of thermal mass in your home and you can put that stranded electricity to work, it may not matter as much that that heat leaves your home overnight. The point is, you're going on sunny days, you're going to have an overabundance of electricity. And then on those hurricane or blizzard scenarios, you may have to hunker down, particularly if you're budget limited. Okay, so let's see. It is 12:36 now. Let's take about a little bit over let's take a 15-minute break. So we'll pick back up at 10 till. And when we pick back up, we'll get back into our sizing discussion and better flesh out our model for getting into the size of our battery bank. So let's take a 15-minute break. We'll be back at 10 till to resume. So we're going to pick back up in about a minute. All right. Welcome back. So what we want to do is generate a graph that shows our consumption, our production, and our battery bank size. Now, you can use commercial solar software to do this. The picture shown is a software called Energy Toolbase, which I think is a particularly good software for commercial solar economics. Generally, for off-grid, I like to do my own modeling, just using PV watts and the customer's electric bill. So, what we'll see is how to generate this kind of graph in a spreadsheet. Maybe it won't look as good. And what we'll use this to do is explore how, our most critical periods of energy. Is it going to be in the summer when you get long days but also heavy air conditioning use, or is it going to be in the winter when you have stormy weather still and lower energy use? And usually it's winter, but it's the other critical time is summer. So what we want to do is figure out how large of a battery we need. And the general premise is you can put a generator on these systems. In fact, you frequently would do that, but using gas to generate electricity, particularly at the small scale, like residential or commercial, it might be all right for a giant power plant, but by the time you scale it down to a home, using gas to generate electricity is still expensive, and it's going to be more expensive than using these low-cost batteries. Yeah, Derek says, will we get a copy of this presentation at the end? You should be able to download it in the handout section, but I do run a YouTube channel, so if you send me an email, I can make sure you get the link to that so you can watch it again if you care to. All right. So when I use a generator, I'm not trying to rely upon the gas generator. There's things we haven't modeled, like extreme weather. PV Watts is showing us typical weather, but there's still outlying weather events. This year was a particularly bad year for solar production, and system production in my region is down by like 15%. So having the generators there to play free safety. You don't need a large generator. The question is, well, a large generator is not that much more expensive than a small generator. And so if you use a large generator, it'll run for fewer hours rather than a small generator. So it's more of a peace of mind situation where, if you're building on a beautiful landscape out in the middle of the woods, you might not want to listen to the generator run all day. Then again, if it's running, it's probably because it's in the middle of winter. You're probably inside. But anyway, if you think you're just going to run off a generator throughout the winter time, that's going to be a very expensive proposition compared to solar and batteries. Pretty much in anywhere except north of Fairbanks, Alaska. So what we do is we run our PV watts model, and we've kind of matched our array so that our array size offsets our winter and summer production on a month-to-month basis. And that will pretty much guarantee us that the solar array will fill the battery back up on a day-to-day basis, except for storm cycles, which is really what we need the larger battery sizing for. And we see that PV Watts has that weather data. And we're going to talk about the battery issues and what this like C20 discharge rate means when we get more into the hardware discussion. And we also know that we have to be on the lookout for tankless water heaters and other surge loads. What we want is a flat load profile. We'll talk about that more tomorrow. But here, what we're doing is we're taking the monthly consumption data, and if we divide it by the number of days in the month, well, then we get how many kilowatt hours per day we're using. And if we divide that by the hours of the day, we get how many kilowatts per hour we're using on average. Now you can say, well, hold on. We just saw these load profiles where the load goes up and then it goes down and then it goes back up and then it goes back down. So we're not going flat throughout the day. And that's when I take a step back and I say, okay, well, the customer is going to be using their energy in the morning, in the midday, and at night, but not really at midnight. Solar is going to be on during the day, and so there might be some times, where there's by modeling the load at being perfectly flat, there's going to be times when we're drawing more power out of that battery, but then there'll also be times when we're not really drawing power out of that battery because of our solar production. We got to start somewhere. So, you take your monthly data, divide by the number of days in the month, divided by the hours in the day. That gives you your average power demand per hour for the month. And what we can see is that, hey, in January and February, the load goes up, and then it goes down in spring, and it goes up in summer, down in fall, up in winter. So we already saw that already reflected in our just basic consumption data. And so what I'll do is for every hour of the year, I'll go back into this PV watts and I'll add a new column. I'll say consumption. And so for, say, let's go ahead and put some filters on here and see if I can't do it in real time. Data, filter. And so we'll say, okay, well, for the month of January and February, we'll do this a little bit basically. Let's just do whole numbers. Let's say for January and February and May and September, and I'm doing 2. So for January, February, May, and September, my consumption is going to be 2 kilowatt hours per hour. So we got our system output in kilowatt hours and our consumption in kilowatt hours. And then we say, okay, well then what's our other times? Well, here we have in March, April, October, November, and I guess we missed December, so let's just call it December 2, just in the interest of time. So March, April, we'll take out June, July, August, and then we'll do fall. Let's just do the rest of fall. We're doing 1 kilowatt hour rather than 2. So that's a little bit basic, but I'm trying to do this a little bit fast. All right. So then for June, July, and August, we'll go ahead and do 3 kilowatt hours per hour. And if I did that correctly, yeah, what we have is for every hour of the year now, a consumption amount. And at that point, I would just start with a guess. And so what we saw earlier, the big, meaty, flooded lead-acid battery is 14, and then 4 of those up to 48 volt is 56 kilowatt hours. So let's just start and guess what a 21 kilowatt solar array and a 56 kilowatt hour battery bank would do. And so we start at 56, and then we subtract, we take our battery state of charge, and then we add our solar array, and then we subtract our consumption. And so what we see is I've drawn 2 kilowatt hours out of it, and we start going down until the solar array hits, and we start going back up. Except that my maximum battery size is 56, and so I want to add an additional, formula here, and I want to say if, all of this stuff is greater than my original starting size, I want to keep it at my original starting size. Otherwise, I want it to be as we had just modeled it. So that's, I think I got all of that done correctly. So let's see. All right. So here is our battery bank for the entire year. Let me try and clean up the numbers a little bit here. And so what we're going to do is explore this to see how negative we get. 122. So our battery bank, starting at 56 kilowatt hours, dips down, and let's go and see when that is. We're scrolling down and scrolling down and scrolling down, and it should be kind of apparent. So here we hit 0, and then the solar array comes back on, and it starts to charge back up again. So what we're going to do now is just kind of do a little bit of guessing. So let's say, what does an 80 kilowatt hour battery bank look like? Well, it goes up. What does a 100 kilowatt hour battery bank look like? And it goes up a little bit, not much. if we go up to 120, now we're getting down to 58. If we can go and explore our system sizes. So like if we do a 14 kilowatt array, negative 775. So obviously, we want something larger. What if we went all the way up to something even more? Oh, there we go. So now we're like, okay, at a 28 kilowatt solar array and a 120 kilowatt hour battery bank, our battery never goes negative. Okay. So what if we went down to 100? Now we're at negative 17. Then we get up to 120. What about if we go even larger? If we go up to a 50 kilowatt battery bank, maybe not. And so what I like doing is just kind of doing a bunch of guess and checking and seeing, where is my, diminishing returns, where maybe I do a 35 kilowatt hour battery bank and then I can get down to a 100 kilowatt hour battery and still not go negative. And then I might go and add a generator runtime column and put in the generator size and see how many hours a day I need to run the generator in order to get the system to be a little bit smaller. And so let's just say what we're going to do now is create our chart for every hour of the day and every month of the year. And so we're going to chart this x-axis here, and we're going to chart our battery bank state of charge here. Yeah. So just bear with me. No. Back up there. Well, let me just, hold on. Should be able to do this. I gotta juggle around my GoToWebinar screen, and when I do that, it kind of messes up a little. So we got our hours. No. Oh, come on. All right, maybe this will just do it like that. If we insert. Yeah, so that's pretty much. Here we have our battery state of charge. And what we can see is that our minimum is not occurring very frequently. It's just our minimum is occurring on the 440th hour. That's like, this is like January 1st, 2nd, 3rd, 4th, 5th, 6th. So this is like on January 20th or so, we're getting down to our bare minimum. And so what I might actually do at this point is say, okay, well, what if we 100 kilowatt hour battery bank's great. You could get away with really not having a generator for this kind of system. But if we did a generator, I would run the generator here, and I would run the generator there, and maybe that would allow us to knock off another 30 kilowatt hours of our battery bank, and just run the generator for a couple of days, and then for the rest of the year we're sitting up at the top for the most part. And so I could probably get away with a 70 kilowatt hour battery bank for an array this size, and be confident in the system, because again, we got the generator there playing free safety. Let me look up the questions. Okay, thanks for letting me know about the audio. So basically what we did is we charted the battery level after making a guess, and then by visually exploring the chart, we could identify that, hey, actually we could reduce the battery bank size by 30 kilowatt hours if we accept a little bit of generator runtime. Okay, so we have a few more questions about, do you want to limit the battery draw to 50%, and what does C20 mean? So we're going to get to those kind of technical discussions when we get into the battery discussion. So we're gonna talk about it, but in general, yeah, the draw from the battery bank is going to be less than 50% on these kinds of off-grid systems. When you're draining the battery by 50%, that means you're draining it over 2 hours. And that is much more typical of how you would use a commercial battery for peak demand management. Whereas a C20 rate would be like discharging the battery at 2 or 3 kilowatt hours of a 100 kilowatt hour battery bank. That's like discharging it by 2 or 3%. It would take us, 100% divided by 2, 50 hours. It would take us 2 days to discharge the battery at a 2 or 3 kilowatt hour rate. That would be like a C48 discharge rate. C20 assumes that you're discharging the battery over 20 hours. And it's really the rating on the battery for how much energy is in it. What we'll learn is that when you discharge a lead acid battery and you drain it by 50% or more, it's going to lose about 2/3 of its storage capacity. Unlike lithium ion, which still does have a declining return the faster you discharge it, but it's not so dramatic. In fact, most lithium ion batteries, their storage capacity is rated at a 2-hour discharge rate. You try and discharge it in 1 hour and it'll store less than that. Same thing with lead acid. It'll become a little bit more clear when we look at some spec sheets. And so what we did is we added a column for the battery level, guessed the battery level, explored the minimum battery level, and then just made some adjustments to our model until we honed in on the right size. And then again, it's nice to have some of in your spreadsheet for you to kind of toggle some things so that you can explore different values and say, okay, well, maybe if I go and do a 70 kilowatt hour battery bank and then I save $4,000 on batteries and I add more solar, adding more solar at this point really is not getting me into substantially more battery life, because the battery is draining during times when it's so duck soup outside that the solar array is hardly doing anything at all. And so commercial solar software like Energy Toolbase will apply optimization algorithms to it to kind of speed up your design process. But this is stuff that you can confidently design just with a spreadsheet. And so, like in the design example in this slide, what I'm looking at is saying, okay, well, increasing the array size from 22 to 28 takes my minimum battery level up by 30, but decreasing it from 22 to, I think there's a typo here. It should be 14. But decreasing it from 22 to 14 takes my minimum battery level down by 600 points. So it is 30 points for the next array size up, down by 600 points for the next array size down. So, you know, for this particular design iteration, 22 kilowatts is pretty good. Maybe 28, only if you have the extra budget, but it's probably would be best just to spend that on increasing your battery size. And then you increase your battery size until this number's no longer negative. And then you might adjust to assume a little bit of generator use. But, you know, again, the goal with a generator is to not need to use it at all. Maybe that means you identify that it's a blizzard outside or that it's a hurricane outside, and so you take it easy on your electrical use during that time and just manually scale things down. Or maybe it means during that unusual weather event, you crank the generator. It says increasing the battery bank size by 32 kilowatt hours. It reduces our deficit by 32 kilowatt hours. So, you know, the battery bank size, unlike the solar array, which has a lot more variability, the battery bank size is kind of more linear. So graphing is graphing and visual exploration. You know, I always try and put it into a narrative to explain what's going on here. Well, oh, I can see it's January, and so what this is a January poor weather system coming in, and this particular day is so bad it really wouldn't matter how large the array is. Nothing's going to get produced on that day, and so we go to the next day, and it's the same thing. And then, oh, the sun comes back up, and then, oh, the sun really comes back up, and then really comes back up, and then we get into kind of a more normal weather pattern, and we almost hit the bottom, and then the sun brings it all the way back up, whereas at this point right here, we would have to crank the generator and take it all the way up to the top. So then, you know, here's like March and April, and what we can see is, okay, aside from a couple of stormy days, most of the time our battery is just cranking along up at the top of its range. You know, not, you know, these are kind of stress-free days where you don't need to worry about your system so much. You know, what kind of surprised, you know, summer, same thing. You know, our array is more than large enough to fill our batteries back up. You know, if the customer wanted to add an electric vehicle, you know, no problem, plenty of capacity here. You know, and so it becomes very apparent what like our kind of multi-day storm cycles. This is 1 day, 2, day 3, day 4, day 5, and then come back up. And so rather than have 5 days worth of storage, it's, you know, that's when we use the generator to crank it all the way back up. You know, once we hit this level, the generator will crank it all the way back up to the top, and then we're going to be falling by an equal amount, but then the generator will crank it back up at the top. And so we use the generator once, we use the generator twice. You know, same thing here. We hit this, we crank it all the way back up to the top, but it still begins to fall. And then we crank it all the way back up to the top, and it'll still begin to, you know, then it'll start to recover again. And so actually, when you think about it, the one like benchmark to assist you with your design is how many times you have to crank the generator to overcome the deficit of the system. And so what I'll do on comparing different system configurations, is it better to have a larger array? Is it better to have a larger battery? Or should we just use the generator? Is I will literally count the amount of time that I'm running the generator and assign a cost to that and say, well, is this generator runtime and the cost acceptable, or should I spend more cost up front to boost the size of my battery bank, usually, so that I don't have to spend so much on gas? So we have a question. So the generator is used to charge the battery and not power the house, and for how long? And so the answer is, for how long, it really just depends on the size of the battery. So this is based around a battery that is, say 90 kilowatt hours. Well, if my battery was 120 kilowatt hours, all this stuff, it would just change the scale of the graph. And so instead of this being my zero line, if I added, let's just make it easy on us, if I added 25 kilowatt hours to the battery bank, now this would be my generator, my zero line. So instead of turning on the generator here, I would turn the generator on here and run it for less time, but I've also spent more money on my battery bank. So then the question is, the generator, is it used to just charge the batteries or to power the house? And it depends on which inverter you use. The higher end systems will allow you to complement the generator and the array so that they can run at the same time. And so if your battery will output 10 kilowatts, you can run the generator in parallel and use the generator capacity to augment the solar capacity. So let's say you were throwing a New Year's Eve party and we're cranking the hot tub and using the oven and just having 100 people over, a higher end system would let you add the two power capacities together, the generator plus the battery. A lower end system, what you would just be using the generator to either charge the battery or bypass the system altogether, such as if there was a component failure, to just run off the generator until that was fixed. So that starts to get into technical discussion. Generally speaking, you're going to be turning the generator on at maybe 80 when the battery doesn't hit zero, but when it hits 20% to go, which is referred to as an 80% depth of discharge. And also, generally speaking, you're not going to use the generator to crank it all the way up to the top because it gets less efficient. We'll talk about that when we get into spec sheets. So you'd incorporate this into your model. And then the question of how long does the generator run? Well, a 10 kilowatt generator will run half as long as a 5 kilowatt generator. So there does become a question of, is it better to have a large generator or a small generator? And that is also a question of component selection. We're going to talk about generators a little bit later, so let's save that discussion till later. So basically, to complete our energy analysis, we've realized that there are days when your off-grid solar array will be producing an overabundance of energy, that generators do play a role in the system. I had an off-grid client who says, look, I want a giant battery bank because even though I'm buying a generator, I'm doing this for peace of mind. And if I hear that generator running, I'm going to think, oh no, I'm about to run out of electricity, and I don't want to have to worry about that. Well, he also bought a very large battery that'll last them for 2 decades, and it was a very expensive system. It was a $80,000 system, which he self-installed. I'm also doing a off-grid cabin that's a $25,000 system. I mean, so you can, they might need to use that generator if they're using their cabin more than just on the weekends. Let's continue the discussion. Okay. So battery selection. Let's start out with some spec sheets. So one of the more confusing aspects of batteries are this like C20, C10, C5 ratings. A lot of forklift batteries are used in 5-hour cycles, so they'll be given a C5 rating. And then a lot of other lead acid batteries that are not used in forklifts, you'll get something a little bit longer, like a C10 or C20. It's not that you have to have a C5 lead acid for a 5-hour cycle or a C20 battery for a 20-hour cycle. It's really like asking someone how quickly they can run the 100-meter dash versus a 5-mile run versus a marathon. It's the same runner in either case, and they're going to have pretty similar speeds along their product class. So like a C5 battery that has a good discharge rate will outperform a battery that, maybe they didn't give you the C5 rating, and so anyway, let's look at some spec sheets and it'll become a little bit more clear. Well, first, we need to understand this chart. This is called a depth of discharge chart that will tell you over on this y-axis is the number of cycles, and over on the x-axis is how deeply you're discharging the battery. And so the way you would use this is you go back to your graph, and you'd say, okay, I am typically, not always, but I'm typically going from let's call that a 90 kilowatt hour battery bank down to a 60. And so I'm typically discharging my battery by, let's just say, 35%. So then I go to my battery depth of discharge curve, and I say, okay, I have an average depth of discharge of 35%. This is 2,000. This is 1,500. If I'm discharging my battery down to 35%, I'm probably going to be getting around 1,600 cycles out of it. If I ran my battery a lot harder and my average depth of discharge was 60%, I would only get 750 cycles out of it. And so the depth of discharge curve will tell you how many cycles you're getting out of your battery. A lot of the lithium-ion batteries dispense with this, and they just, like the Tesla Powerwall just gives you a warranty for how many kilowatt hours come out of it. Well, the Tesla Powerwall has current transducers inside it that are actually measuring the current coming out of it, which your lead acid battery out of the box doesn't have. The Tesla Powerwall also has very strict temperature regulation requirements, that the lead acid battery has a little bit more flexible range. And so this is like the old school way to give you an idea of how long the battery would last, whereas the lithium ion batteries are installed in more controlled environments, and so they can be more exact with their warranties. What I think is interesting about these three charts, here's one where at a 20% depth of discharge, the battery's rated for 5,000 cycles. Here's a different one at 20% where the battery's rated for 4,000 cycles. I know those are a little bit hard to read. And here's one at 20% where the battery's rated for 2,700 cycles. Well, guess what? Every one of these batteries, this one, and this one, they are 3 different lead acid batteries. And so there's no just one lead acid battery. There's a huge product range of lead acid batteries. This one is a sealed battery, and it only has a limited cycle life. This one with 5,000 cycles has a very smooth kind of curb, whereas this one with 4,000 cycles, the curb's a little bit more bendy, and this one's a little bit more bendy. Let's see, skipping ahead a little bit so that we can talk about the bendiness of these curbs. There is a range on lead acid that you do not want to operate the battery at. And I think of it, I'm a mechanical engineer, I think of it like stress and strain. It's okay to stress the battery, it's not okay to strain the battery. And so you get these 3 terms: float, absorb, and bulk. The float refers to this little top of the range between 20% and 0%. And what happens in the float range is that charging the battery all the way up to its maximum top, you start to get to a point where you're just trying to push energy into it, and it can't accept it anymore, so it just gets slightly more and slightly more and slightly more, but then it immediately drops back down again. It's almost like if you're overfilling a bathtub and then all of a sudden you turn a fire hose onto it, the water level will go up, but as soon as the fire hose goes off, the water shrinks back down to the bathtub level because you're just not pummeling it with energy anymore. Actually, for conditioning and maintenance, when you pummel the battery with energy, that helps bust some of the barnacles that cover the plates of the batteries off. And it's that plating of the battery that reduces its life. And so during your maintenance cycles, you're overcharging the batteries at high voltage to maintain them. We're going to come back to that because you can't do that with all the batteries. Guess which batteries you can't pummel with energy to maintain them? The 2 options are sealed batteries versus unsealed batteries. The sealed batteries you cannot maintain like you can the unsealed batteries because all the gas and barnacles and particulate stays in the sealed battery, whereas in an unsealed it gets released as gas. And that gas you have to manage, you have to vent to the outside, but the flip side is the battery will be in better shape and it'll last a lot longer. And so the sealed batteries are marketed as zero maintenance, but it also means less life and higher cost, at least for upfront cost. So there's a purpose for a maintenance-free battery. But if you really want the cost effectiveness, you're going to have to do a little bit of maintenance. Okay, back to the float. So the float is like this little top range. Then we get to the absorb and the bulk, which I would say is the difference between stress and strain. And where that line is, where that fine line is, you can actually see it on this chart, which is kind of when it stops being a straight line and starts to bend. That's my non-scientific way of telling you what the usable range of a battery is. And so here's a battery where that bending point really doesn't start until 60, 65%, whereas in this one, it's more closer to, say, 40%. Well, guess what? Which one of these two batteries is a top shelf lead acid versus a bottom shelf lead acid? Well, the one that you have a much longer range where you can charge and discharge and charge and discharge the battery without breaking it, that's the top shelf battery, where you can use 65% of its range. And then here's the more mid-tier battery where you can only use about 40% of its range. Now, what happens if you cross this point? Well, when you're operating in this part of the battery, that's when there's more plating that's going to go on in the anode of the battery. That's when more barnacles will cover the plating. And as soon as those plates get covered up in barnacles, you can't push electrons through them anymore. And so it's okay to have a little bit of operation in this time, but you don't want to be operating down here on a regular basis. And so what I look at this as is this is the reserve capacity. This is the capacity that you have for those hurricanes and winter storms, but you don't really want to use it if you don't have to. But still, even so, you know, the manufacturers give you a cycle life related to your warranty when you're operating down in that range. I mean, there's this idea that if you fully discharge a lead acid battery, it won't charge all the way back up again, but it's like that's not the whole picture. You know, your battery manufacturer will say, no, you can discharge them a few times. You know, you can discharge it 1,000 times and it'll charge back up again. It just won't do that 5,000 times. And so it's not generally cost effective to operate the battery down in the bottom of this range. And so when you hit this range, that's when the generator turns on. And so I might use a top shelf lead acid, and once my battery hits a 75% depth of discharge, that's when I'll click the generator and charge it back up to somewhere in here, and then I'll let solar take it away from there. What you want to do is every time you get down into this bulk state of charge, that's when you want to click the generator on and come back up again. And if you don't want to have a generator at all, then you want to stay within this range for the most part and only use this range for reliability. And this is what I think is a little bit disingenuous when lithium-ion manufacturers say, oh, well, you know, you can use 100% of the range of a lithium-ion battery, so you can get away with a smaller battery. Well, that's really not true when it comes to off-grid. I mean, if I get a lithium-ion range that's, you know, 40% the size, and I can go up and down and up and down and up and down, well, I can still do that with a high-end lead acid, But what I miss out on is having this reserve capacity if I really, really need it. So let's continue our discussion. Now, the Tesla Powerwall, for that matter, keeps a little bit of reserve capacity because technically, if you discharge a lithium-ion battery all the way down to zero, it literally won't charge back up again. You know, you might be able to resurrect a lead acid, but the lithium ion, if they fully discharge, they don't charge back up again. So it's almost like this, I don't know, this subconscious weakness of lithium ion that they transfer onto lead acid. But Tesla Powerwall is like a 14 kilowatt hour battery, and its usable capacity is 13 and a half. So they just list it at a lesser rating and say you can use 100% of it. So they give you a 5 kilowatt output rating, which means you really can't use this battery at a 50% depth, 50% discharge rate. You know, it does have a little bit of a burst mode, but it'll, you know, it limits you. They kind of take a Macintosh Apple approach where they limit the functionality of the system to improve the overall user experience and force the system to stay within its operating parameters. You know, I'm starting to use cheaper and cheaper and cheaper battery inverters, some of which do not have very good reputations, but I suspect it's because people are trying to use them outdoors in hot, humid, dusty conditions when the battery inverter that I use, which is cheap, really should be going inside in a ventilated, air-conditioned, dust-free environment. You know, so generally speaking, the American battery inverters are very rugged and robust and can go outside and also very expensive, whereas the Chinese inverters are cheap. It's not to say they're worse, but they have to be in a better environment. I find that I want my batteries and my inverters and components to be in that better environment anyway, so I don't need the cost of a more robust shell. But the real fact of the matter is lithium ion is still expensive, and even though the battery price of lithium ion is dropping, the hardware of the proprietary inverter manufacturers is not dropping, and that's where the major expense is. And so, you know, maybe when you buy Tesla Powerwall, only 40% of the cost is the battery, and the rest of it is their research and development and hardware of the Powerwall itself, and then you have to buy the additional interconnection equipment. And so you look at the price of a Tesla Powerwall and you say, okay, $6,600 in hardware. It's probably going to be more than this when you get into the installed cost. You divide it by its rated output capacity, and it's costing, you know, about twice as much as high-end lead acid. And I just think that given the choice between having a maintenance-free battery or a battery that has twice as much usable capacity, off-gridders will find that they have to go for the capacity and do a little bit of maintenance. We'll talk about maintenance later. Now, when you look at that doubling of price, that's $6,600, and you look at their warranty of 38,000 kilowatt hours, the cycle cost of the battery is 17 cents a kilowatt hour, and that means day trading of electricity is really not going to be cost effective at all for residential, and also it's going to be kind of an expensive off-grid setup as well, more than what you're used to paying on your electric bill. So, I think the lithium-ion batteries are great. I don't think that they're suitable for large residential off-grid. What they're really useful for, what they're really designed for, is discharging over a 2-hour period. That's not off-grid living. Off-grid living, you're discharging it over a 20-hour period, and then the sun's up for 4 hours or so. So, we spend a lot more time on lithium-ion technology in our commercial solar peaker class, and get in all sorts of stuff. And what it turns out is the Tesla Powerwall is actually low-end lithium-ion, and there's higher-end lithium-ion that is twice as good and costs twice as much as the low-end lithium-ion. And what I think gets lost in this is the same thing. There's a low-end and mid-range and high-end lead acid. And even the lead acid batteries that are marketed as solar lead acid are not necessarily high-end lead acid. And so here's that bulk absorb float chart, or the cycle chart, or however you want to represent it, comparing the number of cycles of the Tesla Powerwall, industrial flooded lead acid, premium flooded lead acid. The premium flooded lead acid is often what's marketed as the top shelf renewable, as opposed to the deep cycle marina or renewable flooded lead acid. So none of these are golf cart batteries. None of these are batteries you buy at Walmart to start your car with. But what we can see is that, to me, the industrial flooded lead acid, which is like forklift batteries, and the only reason why I would pause to call them forklift is, I buy mine from a forklift manufacturer, but they make it, forklift batteries are usually 36 volts, sometimes 48 volts. And they come bundled together in one cartridge that is heavy as can be, to the point where moving it around gets very difficult. And so this forklift manufacturer will take their forklift battery, and instead of having it be a 48-volt shell, they'll put it in a 12-volt shell. So you're basically buying 4 12-volt batteries instead of one 48-volt battery, and it just makes it 1/4 the weight of each individual section, so that you can actually lift it and move it around. But it's a forklift battery in a 12-volt package. And what I think is interesting about that industrial flooded lead acid battery technology is that it is more like the performance of the Tesla Powerwall 2 than what is being marketed at the trade shows as solar lead acid. Now, you do get what you pay for. I mean, a battery that lasts twice as long is probably going to cost you twice as much. And so, sometimes, where we kind of erred on my first off-grid design is we went for a well-sized industrial flooded lead acid battery, and it's going to last for decades based on its average depth of discharge. Whereas some customers choose to go with lower end flooded lead acid, or even bargain bin flooded lead acid, which is a very low performance battery, just to buy a few more years down the road for the price of lithium ion to drop. So, when in my client, on my first client's case, he said, well, I don't want to replace my batteries 10 years from now. I want to do this once for them to last as long as possible. Well, then I had another client who didn't have any budget. And so we went with a refurbished forklift battery so that we were still using, so that we were, instead of having a battery that would last 20 years, we went with a refurbished brand, which, if we get 10 years out of it, we'll feel pretty lucky. It costs half the price being refurbished. And, the idea being, well, let's just kick the can down the road another 10 years and then see where lithium ion is at that point. And so I just think that it's just interesting that there are some lead acid batteries that are closer to lithium ion in terms of performance than other lead acids. So there's a huge range within lead acid. It keeps going on up when you get into higher end lithium ion. So they actually updated the spec sheet of this one battery, and my jaw kind of dropped. This is where I took the cycle rating off of their manual, and the battery manufacturers, the industrial battery manufacturers are let's see. I don't want to misspeak, so let me. Well, anyway, it's more of I'll pull that back up after when we start tomorrow. But the cycle rating is actually much higher than this. It's something like 3,000 cycles at an 80% depth of discharge now. Well, $200 a kilowatt hour. So we see this 80% depth of discharge rating at 2,100 cycles over 10 years and a bunch of other things. We look at the Tesla Powerwall 2 costing $6,600 in hardware, with its warranty coming out to be 17.5 cents a kilowatt hour. Then we look at the industrial flooded lead acid costing $200 a kilowatt hour at 2,100 cycles at an 80% depth of discharge, and we get to 12 cents a kilowatt hour, which is actually less now because the cycle rating has improved. So now we're finally on this, what does the C20, C10, C5 stuff mean? And what we can see from the spec sheets is that within the battery product line, we have an amp hour rating if we were discharging the battery over 20 hours. That's on this bottom one, 1850. If we sped up the rate of discharge and fully discharged over 10 hours rather than 20, we would only get 1,682 amp hours out of it. And so that's literally, if we cut the cycle time in half, we lose 10% of the capacity. Well, then look, if we discharge it over 5 hours instead of 20 hours, we're losing a little over 20% of the capacity. And then if you notice, there's no C2 rating. There's no 2-hour rate. Well, if I go to my battery and I discharge it over 2 hours, it's not like I won't be able to do that. It's almost like when you take that paper clip and you hold it on both sides of the battery, and that paper clip starts to heat up really fast. The problem with doing that is you're just going to generate a whole bunch of heat. And so that's where the amp hours are going. That's where you're losing it. Now, this is not the same as the batteries that were exploding airplanes out of the sky because they were getting too hot. That's a low-end lithium-ion issue that's separate from just generating heat with lead acid because you're discharging it too fast. Nobody's flying 4,000-pound batteries all over the world. What we can see is that lead acid has this logarithmic decay curve that really starts hitting once you get to a C20. And then a C10 would be here, and then a C5 would be here. Then by the time you get to a C2, you're pretty much everything coming out of that lead acid is going to be heat. And so you just don't use lead acid for loads that are 2 hours or less. Whereas the lithium-ion curve would look much flatter, but it does still drop off at some point, and that's where you get into other kinds of battery technology or even mechanical things like supercapacitors or flywheels. And so the sales rep who's telling you the Tesla Powerwall is more cost effective is not lying. If I took this industrial flooded lead acid, which is much cheaper at a 20-hour discharge rate, and I discharged it over a 2-hour period, I would lose so much in heat that the effective rate of the battery would cost more than the lithium ion. But when you live off grid, you don't need a 2-hour load. You might for a tankless water heater, but when you live off grid, you have that 20-hour load you need to consider. And so, that's when you're looking at the cost differential between 12 cents and 18 cents versus something more than that. All right, so I'm very strong on off-grid for lead acid. Small off-grid, tiny homes, little trailers, cabins that are part-time use. Maybe getting into lithium-ion might be worthwhile for that. I'm talking about whole house power. So this is kind of interesting. The industrial flooded lead acid batteries compared to a non-industrial flooded lead acid weigh a lot more per kilowatt hour. They're more dense. Their plates have more lead in them. They're just higher quality through and through, with weight being a quality indicator. The problem with industrial lead acid, and this is where customers get away from industrial lead acid, is that it's incredibly heavy. So we're going to look at some of this, but generally you have to use either what's called a battery crane, which these things can. We actually, for the battery crane on this particular off-grid site, we had to rent a special forklift to get the things off the truck, because the lift gate of the truck was only rated for 3,000 pounds, and these things weighed 800 pounds each. Then we moved them into the garage, and the client bought a battery crane to move the batteries around. And he actually was kind of happy with that, because when they moved his safe into the house, they had to use the battery crane to pick up the safe and move it around. They couldn't figure out how to do it otherwise. So he found some other uses for that. You don't have to use a battery crane. You don't have to use an industrial forklift. You just have to do a little bit more planning in advance. If you're using an actual forklift battery, you will. But if you're using the 12-volt ones that come in 800-pound packages, there's, your general contractor, construction manager can figure out how to rig a hoist and pick the batteries up 800 pounds by 800 pounds. And so, like, here is a sealed flooded lead acid. So I asked this guy, why did they use sealed? It's not as cost effective. It's more expensive. And he says, well, they doesn't want to do any maintenance, and he has the money for it. Okay, that's a good reason. Not all clients have unlimited budgets, but some do, and so so that's what they went for. Now, this is a pretty cool little rig. This is a 2,000-pound hoist, and he's picking up an 800-pound battery just using his ladder as the battery crane. And so you can see how he went down into the basement and then used a dolly to move it across to about this point, and then picked the battery up with his hoist and just slid it into his battery rack. Now, in our model, we came up with a figure around like 90 kilowatt hours or 70. I don't remember exactly what it was. But what we saw is that within our industrial battery line, and here we go. I was wondering when this would show up. Here's a 12-volt battery. And this is kind of their sweet spot range. It goes all the way up to 1,690 amps, although these weigh a lot. Let's see if I got the poundage on it. I know, you'll just have to take me at my word. These are like around 800 pounds each. And these are around 600 pounds each. And these get up to like 1,000 pounds each. Well, okay. It's 12 volts. $1,690 amp hours times 12 volts is 20 kilowatt hours. So let's say we strung 4 of these up together in one 48 volt circuit. that would be 80 kilowatt hours. Well, what would happen if I needed 90 kilowatt hours or 100 kilowatt hours? And it looks like the maximum is 80. Well, that's when you start adding multiple circuits of batteries and not just have one circuit. So it is common, it is best just to have one circuit. And the reason is, with batteries, you want the resistance on this home run between the battery and the inverter to be uniform so that the same amount of current is drawn out of it. If you only have one circuit, it's impossible to mess up. If you have two circuits and you're pulling it out of that, the resistance in both circuits are going to be separate from each other, and that's going to result in the two battery circuits degrading at different rates. And when one battery cell starts to go bad, it has a cascading effect with it. And so if you had three circuits of batteries, then the problem gets even worse because the resistance on this long furthest away circuit, the more parallel circuits you have, the more mismatch you're going to have between your circuits, and the more degradation of these batteries is going to occur. And so, for the most part, your battery inverter is going to, or your battery manufacturer is going to say no more than 3 parallel circuits. We prefer 2, and then your battery, diehard fans are going to say no, just do 1. So when you have 3 circuits coming into the same terminal block, you got to fuse them. You don't have to fuse them if you have 2. And then 1, you wouldn't either. But with 1, you get into that upper limit of how many kilowatt hours you can fit on a given circuit. So let's see. So sometimes you want to take a look at that weight and say, okay, well, if I know I'm going to have 2 circuits because I'm over 80 kilowatt hours, then I don't need the big heavy one. Maybe I can get the smaller one that's going to be a little bit easier to handle. There is a minimum size of a battery that you can have on your inverter. So generally that's found in your inverter manual. But typically, if you say try and discharge your battery over a 15-minute window and it's lead acid, you're going to get no effective capacity out of it. You're not, when I was younger, I bought a battery and an inverter, and I thought, oh, I could power a boat lift with this thing. But the wattage of the boat lift was such that it would drain my battery, in a 15-minute time frame. My battery was not large enough, and so as soon as you'd flick the switch, the voltage in the battery would drop down, and nothing would happen. The boat lift would not work. Maintaining flooded lead acid is is a lot easier than it sounds. Basically, you have to put water into them, and they sell these little watering kits that fit in so that, this is basically a glorified super soaker. It's a water tank with a pressure hose on it and a little nozzle that you can put into here to fill each cell up with water. You don't actually have to have that. It just makes things a little bit easier to speed up the maintenance rather than screwing and unscrewing each little cap that line the batteries. But you have to use you can't use tap water. It has to be sediment free. So distilled water is the best. What we're doing on my 2 recent projects is we're putting in an air conditioner inside the battery box to provide heat in the winter, keep the battery box cool in the summer, programming it so that it only runs on stranded electricity, so it's not really increasing any electrical usage of the system. And then we're capturing the water from the air conditioner into a tank so that the water's there on site, which is useful to me because if I'm maintaining these batteries, hauling around a bunch of distilled water is kind of tedious. So I'd rather it just be there right next to the battery. And so there are ways to even make these watering systems completely automated. But generally, from talking with installers, it's a maintenance task that the homeowner will eventually want to do themselves just because it's simple. It's much easier than changing the oil on your car. The most tedious part of the battery maintenance is measuring the specific gravity of the battery. And so the battery has individual cells. See these holes inside the battery? And those holes are where the watering kit would go. And so like the one kind of complaint that my first customer had is that in order to stick the hydrometer into the hole, he has to take the watering kit out and then put the watering kit back in. So the watering kit didn't make things, easy on him. It just saved him a little bit of time, not a lot of time, because he's having to read each cell anyway. It's not that big of a deal. I mean, the watering kit waters multiple points in the battery, and you only need to read one point in the battery on an annual basis, and then you rotate. So you can see this battery has 1, 2, 3, 4 holes. They would all get their little watering kit plug in them. And then generally for maintenance, you're just reading one cell. And then the next year you read the next cell. And the next year you read the next cell, and you just rotate it. And so what we see is that here's like a higher end digital hydrometer that costs $1,000 and could probably fit through the watering kits, but the little cheap $20 manual hydrometers are thick, and you gotta take that cap off. So maybe that went over some people's heads, but it's something to look out for if you're actually moving forward with a project. I talked with my battery manufacturer. I said, look, they don't have to do this on lithium-ion batteries, which are sealed, so you wouldn't be able to do it anyway. Well, I said, well, look, if I put current transducers on my battery and I'm building a dust-free, temperature-regulated battery box, do I have to read the specific gravity of the cells, which the warranty says is a every 2-week task? And so I've actually gotten permission from my battery manufacturer not to have to do that every 2 weeks, but to only do it a couple of times a year because of regulating and monitoring and controlling the battery like a lithium ion. Okay, so we are kind of at the end of our time for today. Didn't make it through the quite the beginning of the agenda, so you might have a couple of quiz questions that we didn't cover yet. Don't worry about it. The quiz is just to log your attendance. If there are questions on the quiz that you're thinking about, we'll just just ask at the beginning of the day tomorrow, and we'll open up with that. But in the spirit of brevity, I'm going to pass it back to Half Moon, and they'll transition you into the quiz.
Okay, great. Thanks, JR. Thanks, everybody in attendance. As JR mentioned, yeah, when we close this down, you'll be kicked over to a brief quiz. Attached to that quiz is an evaluation of our webinar procedures and content. So if we do appreciate any feedback you can give us. So please, if you have time, fill that out to the best of your ability. If you don't want to take the quiz right now, everybody will receive it via email in approximately 1 hour. Everybody gets that email, so you certainly don't have to take it twice. Just gives you a second chance to access it. That's all I have. We continue on tomorrow, as JR alluded to. So if you're not signed up for that session, yeah, certainly go to our website, or you can call into our office and we can help you out there. But I believe we'll see the majority of you tomorrow. Okay. Have a good day. Thanks.